The title of the paper I'm presenting is Efficient Processing of Deep Neural Networks, a Tutorial and Survey. This is a comprehensive article that aims to discuss recent advances toward the goal of enabling efficient processing of DNNs. It will give an overview of the DNNs and discuss different hardware and architectures that support DNNs. It also discusses the trends in reducing the computation cost of DNNs through software and hardware changes. It also discusses important benchmarking metrics and design considerations that should be used for evaluating the growing number of DNNs. The paper is organized into several sections. First, a background is provided on the DNN's history and applications, and then an overview of the basic components of DNNs and popular models in use at the time. There is a section that discusses different resources utilized for DNN research and development, and the paper also discusses optimizations to improve throughput and energy efficiency without impacting application accuracy. Near data processing is discussed that addresses the expensive data movements in DNNs. In the end, key metrics for comparing different DNN software and hardware designs are discussed. The use of DNNs is called deep learning, which is a subset of AI that aims to create intelligent machines capable of achieving human-like goals. The significance of deep learning in the context of machine learning is that it enables computers to learn without being explicitly programmed. This is very different from traditional purpose-built programs that rely on handcraft heuristics for behavior. Also, a single machine learning algorithm can be trained to handle different new problems. The neural network belongs to the area of brain-inspired computation, and the basic elements of a neural network, such as the input, weight, activation function, and bias, closely follow the structures of the neuron in the brain. The article also contrasts between the neural network and spiking computing, and points out that the computation in spiking computing also takes into account factors such as the arrival time of the pulse. In this section, simple concepts of the neural network are introduced. Starting from the layers in the neural network, the layers between the first or input layer and the output layer are called the hidden layer. In each of these middle layers, a weighted sum of the input value is computed, and then it undergoes a nonlinear function before it's propagated to the next layer. In the formula on the right that describes this operation, the W, X, and Y are called the weights, input activations, and output activations. The term deep learning is used for neural networks with more than 3 layers, which means more than one hidden layer. But the typical numbers of neural network layers used in deep learning will range from 5 to more than 1,000. In the case of visual data processing, the input layer in the network provides the lowest level features, while subsequent layers produce consecutively higher level features. At the output, the deep network hierarchy provides a probability that these high-level features correspond to certain objects or scenes. The next section clarifies the concepts of inference and training. To put simply, to determine the value of the weights and bias in the network is called training, whereas running the program with the trained weights and produce predictions is referred to as inference.
The main goal of training a DNN is to find the weights that maximize the correct class score and minimize the incorrect ones. This is achieved by minimizing the average loss over a large training set. The weights are updated using gradient descent, which relies on the partial derivatives of the loss with respect to each weight. Backpropagation is a computation which is derived from the chain rule of calculus, is utilized to efficiently compute these partial derivatives. The concept of batch processing is introduced, where multiple sets of input are processed before updating the weights in order to speed up and stabilize training. Also, approaches such as supervised, unsupervised, and semi-supervised learning involving different degrees of labeling in the training set are discussed. Also, reinforcement training is a method used to optimize actions for the max expected reward. Fine-tuning is used when there are previously trained weights and adjustment is needed for a new task or for a new constraint. The next section focuses on the development history, application, and different deployment scenarios of the DNN. The concept of neural networks was proposed in the 1940s but the first practical application utilizing multiple digital neurons did not emerge until the late 1980s with the LeNet network for handwritten digit recognition. The early 2010s marked a significant breakthrough in the field, with applications such as Microsoft's speech recognition system in 2011 and the AlexNet system for image recognition in 2012. The growth of deep learning was further demonstrated by the ImageNet challenge, with the accuracy of algorithms experiencing substantial improvements over the years. There was a notable increase in the participants of the challenge utilizing GPUs for their high compute capability. In 2015, the winning entry of the ImageNet challenge, ResNet, achieved accuracy surpassing human-level performance with a top 5 error rate below 5%. Subsequently, the error rate dropped below 3%, leading to a focus shift to more challenging problems such as object detection and localization. There is wide-ranging impact of the deep neural networks in various fields. In image and video processing, DNNs have significantly enhanced computer vision tasks, including image classification, object localization and detection, image segmentation, and action recognition. DNNs have also improved the accuracy of speech recognition, machine translation, natural language processing, and audio generation. In the medical field, DNNs have contributed to advancements in genomics for gaining insights into the genetics of diseases such as autism, cancers, and spinal muscular atrophy. They have also been utilized in medical imaging for the detection of various types of cancer. Furthermore, DNNs have demonstrated effectiveness in robotic applications, including tasks such as grasping with a robotic arm, motion planning for ground robots, visual navigation, control to mobilize a quadcopter, and driving strategies for autonomous vehicles. The training of DNN models often require large datasets and significant computational resources for multiple weight update iterations, and typically takes several hours to multiple days, and is therefore commonly performed in the cloud. Inference, on the other hand, can occur either in the cloud or at the edge, such as in IoT or mobile devices. For many applications, it is desired to have the DNN inference processing near the sensor. For instance, in computer vision applications, extracting meaningful information from the video at the image sensor can reduce communication costs. Also, for applications such as autonomous vehicles, drone navigation, and robotics, local processing is preferred due to high latency and security risks associated with the cloud. Furthermore, it can be desirable to perform recognition on electronic devices such as smartphones themselves, rather than in the cloud, to reduce latency, decrease connectivity dependency, and improve privacy and security. This section gives an overview of DNNs. First, in terms of data flow, a distinction is made between feed-forward and recurrent networks. Feed-forward network performs computation as a sequence of operations on the output of the previous layer without memory, and recurrent neural networks have internal memory to allow long-term dependencies to affect the output. It also discusses the idea of fully connected layers versus sparse layers. In fully connected layers, all output activations are composed of a weighted sum of all input activations, and sparsely connected layers can be achieved by removing some connections between activations. And the convolutional layer is introduced as an extremely popular form of weight sharing, where the computation is performed using only a small neighborhood of input activations and the same set of weights shared for every output. A common form of deep neural network is the convolutional neural network, or CNN, which consists of multiple convolutional layers. In this type of network, each convolutional layer generates a higher-level abstraction of the input data known as a feature map. These networks can achieve superior performance by employing a deep hierarchy of layers and are widely used in various applications such as image understanding, speech recognition, gameplay, and robotics. The convolutional layers in the CNNs primarily consist of high-dimensional convolutions, where input activations of a layer are structured as a set of 2D input feature maps. Each channel is convolved with a distinct 2D filter from the stack of filters, which is seen as a 3D filter. The convolution results are then summed across all the channels and becomes one channel of the output feature map. And additional 3D filters can be used on the same input to create additional output channels. Multiple input feature maps also may be processed together as a batch to potentially improve the reuse of filter weights. It is reiterated that filters consist of weights, and input and output feature maps are composed of activations. Also, after the 5 to more than 1,000 convolutional layers, a small number of fully connected layers follow, for classification purposes. Several types of nonlinear activation functions, such as sigmoid, ReLU, and several variants of ReLU, max out, are discussed in the paper. ReLU and its variants are getting more attention because of its simplicity, accuracy, and speed. Also, pooling is a method to reduce the dimensionality of a feature map, and it enables the network to be robust and invariant to small shifts and distortions. Additionally, the layer input distribution can be normalized to zero mean and unit standard deviation to significantly speed up training and improve accuracy. In batch normalization, the distribution is further scaled and shifted with the corresponding parameters learned from training. Batch normalization is often performed between a convolutional or fully connected layer and the nonlinear function.
The next section provides an overview of various popular deep neural network models, with the focus on LeNet, AlexNet, Overfeed, VGG16, GoogleNet, and ResNet. LeNet is one of the first CNN approaches designed for digit classification in grayscale images. It consists of 2 convolutional layers and 2 fully connected layers, using small filter sizes and average pooling. AlexNet is the first CNN to win the ImageNet challenge. It contains 5 convolutional layers and 3 fully connected layers, with larger filter sizes and max pooling. Overfeed has similarities to AlexNet, with increased filters and input size, which result in more weights and MACs. VGG16 and 19 go deeper with 16 and 19 layers respectively, balancing the cost of depth with larger filter sizes built from smaller ones to reduce the number of weights. GoogleNet introduces an inception module with parallel connections using different sized filters to process input at multiple scales for improved speed. ResNet exceeds human-level accuracy in the ImageNet challenge. It uses residual connections to address the vanishing gradient problem and allows the network to go even deeper. It also adopts the use of 1x1 filters to reduce the number of weight parameters. In the next sections, popular DNN development frameworks and popular datasets are listed, which from today's point of view are somewhat out of date. Currently, the 2 most used frameworks are PyTorch and TensorFlow. Notably, Keras is still multi-backend and supports both of these frameworks. The popular datasets for classification listed are MNIST, CIFAR, and ImageNet. These datasets have different image sizes as well as different numbers of classes. The development of DNNs has led to impressive accuracy in image classification tasks. As a result, the ImageNet challenge has shifted focus to more challenging tasks such as single object localization and object detection. And beyond ImageNet, there are also other popular image datasets for computer vision tasks. For example, there's Pascal VOC dataset for object detection, and the MS COCO dataset for object detection, segmentation, and recognition in context. Larger datasets are also prepared by big companies like Google, who has produced its own image, video, and audio datasets. Due to the growing popularity of DNNs, various hardware platforms have incorporated features tailored to enhance DNN processing. The fundamental components of both the convolutional and fully connected layers are the multiply and accumulate, or MAC, operations, which can be easily parallelized. Both temporal and spatial architectures are commonly utilized to achieve high performance. Temporal architectures, most used in CPUs and GPUs, employ techniques such as SIMD and SIMT to enhance parallelism. On the other hand, spatial architectures commonly found in ASIC and FPGA-based designs utilize data flow processing, which enables direct communication between ALUs in a processing chain. Apart from parallelization techniques such as SIMD and SIMT, CPUs and GPUs can also cast the convolution operation in the convolutional layer to a matrix multiplication operation. This is desirable because there exist many optimized libraries for multiplication on the CPU and GPU. But on the flip side, it can cause more data redundancy because of the layout of the matrix, and also cause complex memory access patterns. Another approach involves using a fast Fourier transform to turn the convolution in the spatial domain into multiplication in the frequency domain. This has the benefit of the reduced number of multiplication operations, but comes at a cost of large storage and bandwidth. The next section focuses on the energy-efficient data flow for DNN accelerators. It highlights the memory access bottleneck for DNN processing, where each multiply-accumulate operation involves multiple memory reads and writes, impacting throughput and energy efficiency, especially when relying on off-chip DRAM. Therefore, the paper investigates data flows that exploit three forms of input data reuse, namely convolutional, feature map, and filter, taking advantage of the hierarchy that includes a global buffer, inter-processing element network, and register file within each processing element. Several types of data flow are introduced. First, there's the wait stationary type, where each wait is read from DRAM into the register file for each processing element, and stays stationary for further accesses. This processing uses the same wait to run as many MACs as possible while the wait is present in the register file. The second type is output stationary and is designed to minimize the energy consumption of reading and writing partial sums by keeping the accumulation of partial sums for the same output activation value local in the register file. The third type of data flow, the no local reuse, allocates all the area to the global buffer instead of local storage in the processing element. It aims to maximize storage capacity and minimize off-chip memory bandwidth. In this data flow, nothing stays stationary inside the processing element array, and this leads to increased traffic on the spatial array and the global buffer for all data types. The last data flow type, row stationary, optimizes for all types of data, including weights, pixels, and partial sums simultaneously. The data flow processes 1D row convolutions in each processing element and keeps the row of filter weights stationary inside the register file, with additional columns of processing elements added until all the rows of output are completed. A comparison across different data flows reveals that the row stationary data flow achieves the lowest total energy consumption by moving most accesses to the lowest level of the memory hierarchy, which has the lowest energy cost per access. The next section is on near data processing and explores the concept of moving compute and data closer to reduce data movement. For DRAM, one approach is the use of embedded DRAM, which brings high-density memory on chip to avoid the high energy cost of switching off-chip capacitance. An alternative approach is the stacking of DRAM on top of the chip using through-silicon vias, which is commonly referred to as 3D memory. Another novel approach to memory-compute integration is by incorporating the compute function into the memory, specifically in the context of SRAM arrays. The multiply and accumulate operations can also be integrated into advanced non-volatile high-density memories by using programmable resistive elements known as memristors. This is achieved by performing multiplication with the resistor's conductance as weight, the voltage as input, and the current as output. Also investigated is the integration of computation with sensors to reduce the energy consumption in applications such as image processing. The focus of the next section is on the co-design of deep neural network models and hardware to jointly optimize accuracy, throughput, energy consumption, and cost. These approaches can be broadly categorized into two main groups. The first involves reducing the precision of operations and operands, which includes transitioning from floating point to fixed point, decreasing the bit width, implementing nonlinear quantization, and incorporating weight sharing strategies. The second category focuses on reducing the number of operations and model size through methods such as compression, pruning, and developing compact network architectures. The final section discusses the importance of considering several key metrics to compare different designs and techniques, including accuracy robustness, power energy consumption, throughput and latency, and cost. Specifically for DNN models, a number of metrics are given. First, accuracy of the model in terms of, for example, the top 5 error on datasets such as the ImageNet, also including the type of data augmentation used. Second, the network architecture of the model, including number of layers, filter sizes, number of filters, and number of channels. Then there's the number of weights, and if possible, the number of non-zero weights. And finally, the number of MAC operations. The paper also specifies a list of metrics for DNN hardware. including the power and energy consumption of the design, the latency and throughput, as well as the cost of the chip.